Imagine feeding a blind person millions of books about color and then asking them to paint a sunset. They do it perfectly, but not because they memorized the word sunset. Deep in their mind, they have constructed a perfect mathematical map of light, temperature, and space. This is the biggest open secret in artificial intelligence. For years, we believed these systems were just fancy autocomplete engines, stitching words together based on probability. But that is where everyone is wrong. Before an AI can speak a single coherent sentence, it must build a highly organized, multidimensional map of our physical reality, a silent, invisible scaffolding of the world. To understand how we know this, we have to look at a brilliant experiment conducted by researchers at Harvard and MIT. They took a language model and trained it on a game called Othello, but they did not give it the rules. They did not show it the board. They only fed it long lists of text transcripts of past games, sequence strings like E3, then F4, then C5. To the model, these were just characters. But when they tested the system, it did not just predict the next likely characters. The researchers looked deep inside the model's active memory and discovered something shocking. The AI had internally reconstructed a perfect, virtual 8x8 grid of the game board. It tracked every white and black piece, updating their positions with every turn. It had built an internal model of a physical reality it had never seen, simply to make sense of the words. This mathematical territory is what scientists call latent space. Think of it as an endless, dark room where every concept, object, and physical property in the universe is assigned a precise coordinate. In our three-dimensional world, we locate a coffee cup using 3 coordinates: height, width, and depth. But an AI uses hundreds, sometimes thousands of dimensions to map a single concept. In this hyperdimensional map, the word warmth is placed mathematically closer to the color red than to the color blue. If you subtract the coordinates for the word man from the word king and add the coordinates for woman, the math points directly to the coordinates for queen. The machine is not copy-pasting definitions. It is navigating a topological map of human experience. This mapping is not just conceptual. It is physical. In another breakthrough study, researchers analyzed a model trained purely on raw text datasets. They extracted the internal representations of geographic locations mentioned in the text. When they plotted these multidimensional points onto a simple 2-dimensional graph, a stunning image emerged. The internal coordinates of the cities formed a nearly perfect geographical map of the world. The model had never looked at a satellite image or studied a globe. Yet, by analyzing how humans talk about places, it mapped the spatial layout of our planet. It did the same with time, creating a linear history timeline where events from the 1920s were mathematically ordered before the 1960s. For years, the recipe for AI progress was simple: add more data, add more computers, and make the models larger. But by mid-20s, developers hit a wall. We have scraped almost all the high-quality text humanity has ever written. Scaling up raw text models is yielding diminishing returns. This has killed the debate about whether these systems are just stochastic parrots that repeat human words. To move beyond this limit, the industry is undergoing a massive shift. The goal is no longer to build systems that learn from our words. The goal is to build systems that learn from our world. How do you teach a machine the physical world without using text? You change how it processes video. If you ask a traditional generative AI to predict the next frame of a video of a windy day, it wastes immense computational power trying to calculate the exact texture and movement of every single leaf. But humans do not do this. When you look at a tree, you do not track every leaf. You understand the abstract concept of a tree blowing in the wind. This is the core of Yann LeCun's Joint Embedding Predictive Architecture, or JEPA. Instead of predicting every pixel, JEPA models predict abstract representations in latent space. They ignore the irrelevant details and focus on the underlying physics. It is the difference between memorizing the static pixels of a falling cup and understanding gravity. This lack of physical understanding is the single greatest bottleneck in robotics today. We can build humanoid hardware with incredible precision, but programming them to navigate a messy, unpredictable kitchen is incredibly difficult. A robot cannot safely pick up a ceramic mug if it does not have an internal model of weight, friction, and fragility. It cannot step over a curb without an intuitive understanding of gravity and inertia. The next generation of robotics is not being trained on code or manuals. They are being trained on hours of raw, multi-sensory video, building that invisible physical scaffolding within their neural networks before they ever take a physical step. The true significance of this shift is profound. We have spent decades viewing artificial intelligence as an author, a conversationalist, or a painter. But these are just the outward expressions of something far deeper. Beneath the text, the images, and the code lies a silent, mathematical geographer, a system that is quietly mapping the physical and conceptual contours of our reality, using the same topological relationships that humans use to navigate existence. The future of automation is not a machine that knows how to talk. It is a machine that finally understands where it is.